Welcome back, guys, to another video. In this lesson, we are going to learn about neutralization reactions. As you may recall from a previous lesson, we have already talked about neutralization and what it represents, which is really just a chemical reaction between an acid and a base. Now, important to know is that in neutralization reactions, our products will be salt and water. And here in the middle of the screen, we have the visual representation of what that would look like. Now, something important, and which is really what this lesson is about, is that salts can be neutral, acidic, or basic. So just because we are using the word neutralization, it does not mean that the pH will actually be neutral, meaning 7. So let's look at a few examples on how we can determine what the products are for a neutralization reaction. So let's look at an example first. So we know that we start with an acid and we start with the base as our reactants. Our products will be a salt and water. So this relates back to the types of chemical reactions that we learned before. So this is really what I want you guys to think about. I want you to find the process that you would have for example, forming water. So we know that at least part of this will have to be H2O. So if we look back at the acid and the base, you guys will notice that we have the hydrogen here and the hydroxide there. So essentially, those two come together to form the water molecule. Now, what is left over is going to be the aluminum and the sulfur. And those two together, right, would form our ionic compound, which is the salt. So the ionic compound is really what we're looking for here. Now, of course, if you recall our previous lessons, we know that ALS is not a correct ionic compound because we have to take into consideration the charges. So we know that based on the location of the periodic table, we have aluminum with the +3 charge and sulfur with a -2 charge. And we know that these have to equal 0. So therefore, we know that this will be a 3 and that will be a 2. Of course, as I've mentioned before, you always need to make sure that your chemical your chemical equations are fully balanced. So I'm not going to go in depth into that right now at this precise moment, but it is important that we understand how we achieve some of these balancing problems. So just a quick check here. Our sulfurs, so we have 3 sulfurs on each side. We have 2 aluminums on each side. We have a total of hydrogens on the reactants. We have 6, and then we have 6 more, so we have a total of 12 hydrogens. So therefore, we need a 6th there. Just double checking with our oxygens, we have a total of 6 on the reactant side, and therefore, we also have 6 on the product side. So really what we just did here is we identified the portions of the acid and the base that would form the water molecule. And then we took the cation and the anions that were left over to produce our ionic compound. Now, of course, I decided to just write the salt first and then the water, but honestly, these two could be switched. I mean, there's no real way that they have to be written down. So let's look at another example. Here we have, again, another neutralization reaction. Now here, we are not given the initial compounds for the acid or the base. We have to write those ourselves. However, we have learned in a previous video how to name, and therefore we know how to work our way backwards to figure out what the compound should be. So hydrochloric acid, we know that that's a binary compound because only binary acids are the ones that use the hydro prefix. So here we're dealing with hydrogen and chlorine. Because, of course, we always have to check charges, that would just be a +1 and a -1, so we don't have to worry about their including anymore. Our base is going to be our calcium hydroxide, so that would be CaOH, and we know that calcium has a charge of +2, and hydroxide, it's a polyatomic that we find in our list, which is going to be a charge of -1. So therefore, we need 2 of them, and because we need 2 of them, and that is a polyatomic, we need to have parentheses with the 2. Now, this is where the neutralization reaction is going to take place. We are going to draw our arrow to signify that a reaction has taken place, and our products are now going to be the salt and the water. So I'm just going to go ahead and write my water. And again, it's just the way I do it, but you can write water first and then the salt. It's no issue about that. Now, the cation and the anion that are left over is our calcium and our chlorine. We always check for charges. Here we notice we need another chlorine, so therefore we write a 2 for subscript. And then here is your neutralization reaction. It is not balanced, however, so we still have to do that. So what I'm going to do here is I am going to multiply my initial acid times 2. So that would give me 2 chlorines. And I now just need to check my carbons are good and my oxygens. For my oxygens, I need a total of 2. On my product side, I'm only showing 1, so I'm going to write a 2 there. Now my hydrogens, I have a total of 4 on the reactant side. And then on the product side, I now also have 4. So we are good. So this is another example of a balanced neutralization reaction that we wrote down based on the names of the acid and the base that were given to us. Now, this next part is for my PreAP students. So if you're a level student, at this point you can go ahead and stop the video. We have covered the extent of neutralization reactions that is required for the curriculum. Now, PreAP students, hang on, we still got a little bit more stuff to learn. Let's get started. We have such a thing as a strong and weak acids and bases. Here on screen, you have the definitions for what strong constitutes and what weak represents. Now, the big idea here is that whenever we take our acids or our bases and we put them in water, there will be a reaction that we call dissociating, meaning the individual acids or bases would, in a way, break apart. So, for example, if we were to have Na and OH, so for example, a base sodium hydroxide, we have the understanding that all of these different elements would dissociate into ions, meaning the Na is going to go by itself, the OH is going to dissociate, and this one's going to have a -1 charge, the sodium is going to have a +1 charge. So that's what I mean by dissociating. So for a strong either acid or base, the same thing for both, they fully dissociate, meaning that because there's going to be this break apart idea in a strong base or a strong acid, they're going to be the maximum amount, essentially 100% of them. So they're just going to break apart. Nothing's going to stay together as a compound. Now, of course, if we're talking about acids, we're talking about the hydrogen ion. And if we're talking about bases, we're talking about the hydroxide ion. So, of course, you do have to keep that in mind. But regardless, we're talking about a full dissociating, full breaking apart. Again, essentially that 100%. But when it comes to the weak acids or bases, there's nowhere near that 100%. They only partially dissociate. So some of them, either the acid or the base that you put in the water, some of them might dissociate, but not thoroughly, the entire thing. And that's what we're looking for. Now, honestly, there's no other way that we can learn about this other than have a reference sheet that has a list of the strong ones, because the list of strong ones is way shorter than the list of the weak ones. So really, we just focus on the strong ones. As long as you have that list, which is right here on screen, you are good to go. This is not every single strong acid and every single strong base in existence. Of course, we're only going to focus on the most common ones. However, anything that is not on this list, go ahead and for my class, we're going to assume that it is a weak. So make sure that this list is something that you have access to, because as we move forward with the video, we are going to be referring back to this particular visual, okay? So I'll give you guys a second to make sure to either take a picture, write it down, and then let's go ahead and move on. So When it comes to neutralization reactions, and kind of cycling back to the initial piece of information I gave you guys, that salts can be neutral, acidic, or basic. Well, how do we determine that? Aside from, of course, maybe we could just memorize all of these equations, which we're not going to do. We have this other idea that when it comes to neutralization reactions, it truly depends on whether the acid and the base that we started with were either strong or weak. So what's going to happen here is that we are going to look at what that pattern is. So if we have an acid that is strong and we react with a strong base, that means that all of the hydrogen ions dissociated, so they're free, and all of the hydroxide ions dissociated, so they're also free. They're going to bond together and form that water, right? And that salt that is left over is not going to have an effect on the pH of that water. So therefore, the salt becomes neutral. Now, what happens if the acid is strong and the base is weak? Well, then that means that all of the hydrogen ions were released, right? They got dissociated, but not all of the hydroxide ions were dissociated. So some of them are still going to be bonded to that original base that they had. So that means that we're going to have some, or at least more, right? We're going to have more hydrogen ions than we do hydroxide ions. And therefore, because there is more hydrogen than the hydroxide, the overall salt is going to be acidic. Now, what happens if the scenario changes? What if the acid is weak and the base is stronger? Well, we know then that all of the hydroxide ions are going to be dissociated, and not all of the hydrogen ions are going to be dissociated. So therefore, we're going to have a lot more hydroxide ions, and therefore, I actually did the wrong sign there. We are going to have, here in this scenario, more hydroxide, and therefore our overall reaction is going to be basic. And of course, I didn't make a chart here, but in every single time we're going to have H2O, which is neutral. So let's look at an example just to put this into practice. And I have included, of course, here at the very top, the visual that we just looked at. So we start with hydrobromic acid and aluminum hydroxide. So we have the water, and then we're going to have our salt, which is going to be aluminum bromide. Now, of course, you always need to make sure that our charges are equal to 0. And we notice here that we need 3 bromines. Now, of course, like always, we need to make sure that things are balanced. So we're going to go ahead and write a 3 here. And that way we can take care of the bromines. Now we look at our aluminum, we have 1. And our oxygens on the reactant side, there's a total of 3 of them. So I'm going to write a 3 here. And then we also started with 3 hydrogens here plus 3 here. So that gives me a total of 6. And therefore here as well, 2 times 3 gives us 6. So we are good, we are balanced. Now let's go ahead and determine the acidity of our salt. So going back to that list of the strong and acids and bases, we need to determine if they are strong or weak, the ones that we have on screen. So hydrobromic acid is a strong acid, so this is strong. Aluminum hydroxide is not part of the list that I gave you guys that were the strong bases, so that base is going to be a weak one. Remember, if it's not on the list, safely assume that it is going to be weak. So we know, of course, that water is going to be neutral because, well, it's water, right? And now we just have to determine the what our salt is. So we have a strong acid and a weak base. So we're dealing with this scenario right here. So therefore, our salt is going to be acidic. So we're going to have an acidic salt. Alrighty, guys, let's do some practice, and I hope you guys enjoyed this video.